All right. So, you know, in the tech world, there's been this buzz lately, and you've probably seen the headlines yourself about Huawei and this whole
Hmm.
thing with them supposedly testing a domestically developed EUV machine in China.
Yeah.
And, it's not just any EUV machine.
Right.
What's got people talking is that it looks like they're going with a completely different light source technology.
Right.
They're calling it laser-induced discharge plasma, or LDP for short.
Yeah. LDP, exactly. That's kind of the hot topic right now. And it's really interesting because it's a completely different approach from what ASML is doing with their laser produced plasma, or LPP, which is kind of the industry standard at the moment.
Right, exactly. And that's why we're here today for this deep dive. We really want to unpack this whole LDP thing and see what it's all about.
Yeah.
We've got this recent analysis that we've been digging into, and yeah, I think there's a lot to learn here.
Yeah, absolutely. I think the mission here is really to kind of understand, what is this LDP approach? Why is it significant that China might be using it? And kind of what's the backstory of this technology as an alternative to the EUV standard that we have today?
Okay, so let's start with the basics. The fundamental challenge here is generating that 13.5 nanometer light for EUV, which, as anyone who follows this stuff knows, is incredibly difficult.
Yeah, it's a huge challenge.
ASML's current method, the LPP that we talked about, involves firing a CO2 laser at a tiny tin droplet.
Yeah.
And they actually do it twice.
Yeah.
The first pulse shapes the droplet, and the second pulse turns it into this super hot plasma that emits the EUV light that we need.
Right. And I think what's fascinating is what happens to that light, because after the plasma is created, it bounces off of a series of mirrors, and we're talking 6 to 10 mirrors here. And each of those mirrors is incredibly precise, but they're only reflecting about 70% of the light that hits them. So by the time you actually get that EUV light to the silicon wafer, you've lost a significant portion of the photons that were originally generated.
So like the initial burst of light is way more powerful than what actually
Yeah.
makes it to the wafer.
Yeah.
You see?
And that's why, you hear all this talk about the huge power requirements for EUV sources.
Yeah.
Well, it's not just about creating the plasma, it's also about overcoming those losses in the optical path.
Right. It's like that initial, you need so much power just to...
You need a lot of power to start with just to get a little bit at the end.
Exactly.
Yeah.
Okay, so LPP is kind of the big player now, but it wasn't the only game in town. Back in the late 90s, early 2000s, researchers were looking at different ways to generate EUV light. And one of the main contenders back then was DPP, discharge-produced plasma.
Yeah, DPP, that was a big one. And, it works on a completely different principle than LPP. Instead of a laser, you're using a really powerful but very short electrical current that you discharge between two electrodes. So basically, you can think of it like a tiny controlled lightning bolt.
Wow, so instead of light, it's
electricity.
Electricity, okay.
Yeah, and to make this whole thing work efficiently, you use a vaporized fuel, and usually it was either xenon or tin, and this fuel is kind of pre-ionized, which makes it easier for the electricity to flow through it.
Okay,
So you have these capacitors that store a ton of energy, and then you release that energy in a really short burst, creating this line of current between the electrodes, and that generates a really strong magnetic field around it.
Okay.
And this magnetic field is where things get really interesting, because it doesn't just sit there. It actually squeezes the ionized fuel inwards. It compresses it into a plasma.
Oh, wow.
And this is what they call the Z-pinch effect. And it basically heats that plasma up to, hundreds of thousands of degrees Celsius.
It's like creating a tiny star almost.
It's like a miniature sun, Yeah, and when it's done just right, that super hot, dense plasma emits a significant amount of EUV radiation, and you can capture that and use it for lithography.
Okay, so it's basically like harnessing the power of fusion or something.
It's kind of like that, yeah.
To make computer chips.
Pretty wild, huh?
Wow, that's incredible. Okay, so in those early days, you had groups like EUVA in Japan, who were looking at xenon as the fuel for DPP, and then you had Philips Extreme UV, who are focusing on tin.
Right.
So what made tin the preferred choice in the end?
Well, it turned out that tin ions were just much more efficient at producing light at that crucial 13.5 nanometer wavelength. And the light was also less likely to be reabsorbed by other tin ions in the plasma.
Oh, so it's like tin was just better at producing the right kind of light.
It was all about efficiency. Tin could basically turn more electricity into usable EUV power.
I see. Okay, so DPP with tin looked really promising, and I think Philips Extreme UV even shipped a DPP-based source back in 2003.
It did, yeah.
But it seems like it ran into some problems, right? Like, it couldn't quite achieve the kind of high repetition rates that you need for mass production of chips.
Yeah, that was a big hurdle, you know, because to make EUV lithography work on an industrial scale, you need to generate thousands of these electrical discharges every second.
Wow.
You know, to get enough light to process a reasonable number of wafers per hour.
Right, you need that throughput.
You need the throughput, exactly. And that kind of speed put a lot of stress on the electrodes. You know, they would get really hot and start to get damaged.
I can imagine.
There's like thousands of tiny lightning strikes happening constantly.
Yeah.
And then there was also the issue of tin vapor condensing on, you know, the cooler parts inside the machine.
Wow.
And so they had to come up with all these complex engineering solutions to heat those surfaces and prevent those kin films from forming because those films could block the EUV light.
Right. So basically, DPP had these kind of practical engineering challenges that were really hard to overcome.
Exactly.
Okay, and this brings us to LDP, laser-induced discharged plasma, the technology that's in the news now with Huawei. And it sounds like this is where Philips Extreme UV kind of built on their work with DPP and tried to address those limitations.
Yeah, that's right. They were looking for ways to kind of combine the best aspects of both DPP and LPP.
Okay.
And so they came up with this hybrid approach with LDP.
Well, what did that look like?
So in those early LDP systems, they used 2 rotating discs made of tin. And these discs were connected to energy storage capacitors, and they also acted as the electrodes.
Okay.
And as these discs were rotating, they would pass through a bath of liquid tin, kind of coating their surfaces.
Okay, so they were constantly getting a fresh coat of tin.
Exactly, yeah. And then a pulse laser would fire at the tin film on one of the discs, creating this little cloud of tin vapor between the electrodes.
So a laser's kind of like setting the stage.
Yeah.
It's like a primer, you know, that electrical discharge.
Exactly. And then, just like in DPP, a large electrical discharge would fire across that gap, creating the Z-pinch and generating that super hot plasma that emits the EUV light.
Okay, I see.
And this rotating disc system had some potential advantages. You know, instead of having to precisely target individual tin droplets like an LPP, the rotating wheels were constantly providing this fresh supply of tin, so the laser always had something to hit.
So it's more efficient in a way.
Potentially, yeah. And dipping those wheels in liquid tin could also help with dissipating the heat from those Z-pinch events.
Right, because those get incredibly hot.
They do, yeah. And I think they also used a foil trap to catch some of the tin debris, which is a big issue in these EUV sources. But of course, that meant sacrificing some light intensity.
Right, it's always a trade-off.
Always a trade-off, yeah.
Okay, so LDP seemed like it had a lot going for it. So why didn't it become the dominant technology? You know, why did ASML go with LPP in the end?
Yeah, that's the million-dollar question, isn't it? And unfortunately, the exact reasons aren't really public knowledge.
Right, they're playing their cards close to their chest.
Exactly. So we have to kind of look at what we do know and make some educated guesses.
Okay.
One of the main theories is that LDP just couldn't ramp up its power output as quickly as LPP.
Okay.
Back in 2008, Extreme announced that they could achieve 500 watts of EUV power at the plasma source.
Okay, that sounds impressive.
It does, but the thing is, what really matters for chip manufacturing speed is the power that reaches the wafer. You know, the power at the intermediate focus after all those mirror reflections.
Right, because you lose so much power along the way.
Exactly, and at that time, Extreme's LDP source only had 14 watts at the intermediate focus.
Yeah, that's what that...
A big difference.
Yeah.
And they thought they could get to maybe 34 watts with a better collector system. But the companies working on LPP like Cymer and Gigaphoton, they were already reporting much higher power levels at that crucial intermediate focus. So to reach a competitive level of, say, 500 watts at the intermediate focus, Extreme calculated that they would theoretically need something like 4,000 watts at the plasma, and they would have to fire 50,000 pulses per second each with a significant amount of energy.
That sounds like a huge engineering challenge.
It does, yeah. And not just engineering. You know, there might have been some fundamental physical limits as well, because earlier research with xenon plasma had shown that past a certain point, adding more power just made the plasma bigger. It didn't actually make it brighter in the direction of the collectors.
Oh, so it's like you're putting in more energy, but you're not getting more usable light.
Exactly. You're just wasting energy, basically.
I see.
And it's possible that a similar issue was happening with the tin plasma in LDP.
Oh.
Extreme did announce 30 watts at the intermediate focus in 2011, but it seems like by then ASML had already seen enough progress with LPP, and they decided to just focus their efforts there.
Okay, so it's like a strategic decision based on where they saw the technology going.
Right. And you know, it's worth noting that even after ASML made that decision, Ushio, they continued to use LDP for some niche applications, like mask blank inspection.
Okay.
And in fact, a paper from 2022 mentioned that their LDP system could achieve around 250 watts at the plasma source.
Okay. That's still pretty good, right?
Yeah, it's respectable, but you have to keep in mind that the power demands for lithography are much higher than for inspection tools.
Right. It's a different ballgame.
Exactly, yeah.
Okay, so now we come to China and their current efforts to develop their own EUV light source technology. And it seems like they're taking a multi-pronged approach.
Yeah.
They're looking at LPP, they're looking at free electron lasers, and they're also revisiting this LDP technology.
Yeah, they're really exploring all their options.
And we've seen some research papers coming out of China from organizations like the Harbin Institute of Technology that are investigating LDP plasma dynamics.
Right, and that research has been going on for a while now, since at least the early 2010s. But from what we can tell from the publicly available information, the conversion efficiencies that they're reporting in these papers don't seem to be significantly better than what was achieved with LDP back in the mid-2000s.
Oh, really?
Yeah, and in some cases, the numbers are even lower.
Interesting.
But of course, we have to remember that what we see in public research might not always reflect the very latest advancements.
Right. They might be holding some things back.
Exactly. Yeah.
Okay, so let's zoom out for a second and recap what we've talked about.
Okay.
We've looked at LPP, the current dominant technology for EUV lithography.
Right.
And we've looked at LDP, this alternative approach that's getting a lot of attention now because of what's happening in China.
Yeah.
We've talked about how these two technologies work at a fundamental level, how they generate that 13.5 nanometer light.
Right.
And we've discussed the historical context behind ASML's decision to go with LPP,
Right.
which seems to have been driven by LPP's potential for scaling power output.
Oh, yeah.
So even though LDP didn't win that initial race, it's clear that research is still ongoing.
Oh, absolutely. Yeah.
And especially in China.
Yeah, especially in China.
And, this kind of highlights the fact that even though we have a clear leader in the EUV lithography space, the underlying challenges are still so immense that there's still room for breakthroughs.
Yeah.
There's still room for alternative solutions.
Absolutely. And I think that's what makes this whole field so exciting. It's like we're still in the early stages of figuring this out.
Exactly.
And who knows what the future holds.
Yeah. And I think for anyone who's following this, it's important to keep an eye on those alternative research paths, especially in places like China, because those could be the source of some really interesting developments in the future.
I agree. Yeah.
It really makes you wonder what the future of microelectronics is going to look like.
It does. Yeah. It's going to be fascinating to see how this all plays out.
Absolutely.
Yeah.
Well, thanks for breaking it all down for us.
No problem. Happy to do it.
All right. That's it for this deep dive. Thanks for listening.
See you next time.